Welcome, my friends. I am so excited because in this video we get to talk about graphical displays of data. Now, traditionally in an intro stat class, you would spend a lot of time creating graphical displays by hand. And one of the most tedious of those would be creating a histogram by hand, which there's a lot of details that kind of go into that, and it takes a long time. And it's really not really worth our time to go through all the details of creating things like histograms and ogives and other things like that by hand. Because, now with the advent of technology, rarely are you ever going to have to actually, take out pencil and paper and create one of these graphical displays. We're usually just going to use technology to create this stuff. So if you're one of my students, you're going to be creating these displays in some kind of statistical software, such as maybe Google Sheets or Excel or maybe R or maybe something else, right? So the focus of this video is just going to be introducing a number of different graphical displays of data. The focus is not going to be on creating them yourselves, but more just understanding what they are and when they should be used. So let's go ahead and get started. Now, one of the most common things that you might be tasked to do is somehow organize quantitative data. And one of the most common ways to do that would be to create what is called a frequency distribution. So I think the best way to show you what that looks like is to just show you an example. So here's an example of a frequency distribution for the variable of commute distance in miles for individuals working in Grand Rapids. And traditionally, this is going to have either 2 or 3 columns. And the first column is going to be just titled class or maybe bin. And this is just kind of groups for your quantitative variable. So really what this is saying is we've kind of grouped our variable into, from 0 to 4, 4 to 8, 8 to 12, 12 to 16, etc. for the number of miles that someone is traveling to get to their job in Grand Rapids. And then we're counting how many observations we have in each of those ranges. So this would say that we have 32 individuals who are traveling from 0 to 4 miles to get to their job, or we have 84 individuals who are traveling 4 to 8 miles, etc. And then we've also calculated what is called the relative frequency, which is just expressing that number as a percentage. Now, we can calculate those relative frequencies by simply taking each frequency and dividing by the total of all frequencies. So in this case, if you were to add up all these frequencies, you would get 450. And if you were to take each of these values and divide by 450, you would get each of these relative frequencies. So let me just show you with maybe an example or two here. So let's just say that we wanted to calculate the very first one here. We would take the 32 and we could divide that by 450, and then we would get the decimal form of the percentage that you see here, which is 7.1%. So this is what we call a frequency distribution, a very common way to organize quantitative data. Now, traditionally in a frequency distribution, the classes are going to be of equal length, sometimes with the exception of maybe the first or the last class. So what I mean by that is kind of going from one class to the next, we're really jumping by the same number. So from 0 to 4, we're going up 4, add 4 again to get to 8, 12, 16, etc. And the one exception might be the last class, and this one has, maybe more numbers in it because it's kind of a catch-all for all the remaining values. And then, as I've already mentioned, you can find that relative frequency column by simply taking each frequency and dividing by the total. Now, what you might do is you might want to graphically display a frequency distribution. And the graphical display of a frequency distribution is what we call a histogram or a frequency histogram. So basically all we've done is taken each of those classes from 0 to 4, 4 to 8, 8 to 12, etc. And we've just graphed those on like a bar type graph with the frequency being the height of each bar. So now this kind of helps us to visualize and say that, oh yeah, the most common driving distance is anywhere from 8 to 12 miles. And as we get to more and more miles, they get to be less and less common. We don't have quite as many people traveling 24, 28 miles compared to some of the lower miles. Now, traditionally on a histogram, the bars should not have any gaps between them. So what I mean by that is right where one bar ends should be where the next bar starts. And that's because we have a shared boundary between each of the bars. So the very first bar ends at 4, and the bar after that is going to start at 4. So since they have this shared boundary, there really should not be any gap between the bars. And some people might point out and say, well, aren't you kind of double counting that 4 then? Well, no, because traditionally you would only include the value the first time you see it. So like the 4s would be included in this bar, but not in the second bar, right? Or the 8s would be included in this bar, but not in the bar after that. So make sure if you're ever making a histogram that the bars do not have any gaps between them. If you had a bar chart, which is a little bit different than a histogram, then you might have some gaps between the bars. You might have a categorical variable, and we'll talk a little bit about that later in this video. Now, the exact shape of the histogram is going to tell us about the distribution of the dataset, a term that I just used a second ago. By distribution, what we mean is what values are possible for that variable and how likely are they to occur. In this case, the values that are possible are, anywhere from 0 all the way up to, greater than 28. And it seems like, the more likely values are somewhere in the, maybe 4 to 16 range. Those are the most likely ranges. So the histogram helps us to easily see the distribution of a data set, right? And there are 5 common distribution shapes that you should be familiar with. And I'm going to show you them here on this slide. This is a very foundational slide, and this is a very important idea or concept. So make sure you're familiar with these 5 different distribution shapes and that you're able to kind of pick them out based on different situations. So the first one, and perhaps the most common distribution shape, is what we call the normal distribution. First, let me just note that I've kind of left off the axes titles here. The vertical axis for every single one of these is going to be the frequency. So like the higher the bar is the more common or more frequently you would see that type of result. And the horizontal axis would be like the classes for your variable, right? So over here would be lower values of the variable, or over towards the right would be higher values of the variable. And if you have a normal distribution, then it looks something like this. You have the most frequent result is going to be right down the middle. And then as you get farther and farther away from that most frequent result, either higher or lower, those values are going to be less and less common, right? So values that are much higher than the middle are going to be not very common, and values that are much smaller than the middle are also going to be not that common compared to the middle. Now, I'm going to use the example of test scores to explain each of these histograms, because depending on the context, test scores could fit any of these 5 distribution shapes. So what would test scores look like if they were to follow a normal distribution? Well, that would mean that whatever the average or middle test score is also the most common. So this would be like, let's say that an 80% is the most common test score. Well, that would go right down the middle. And then as we move to either higher or lower test scores, those would become less and less common. So maybe the most common test score is 80%, and then maybe like 90, 95% is over here to the right. So these bars are not quite as high as the middle. So that means like, maybe 90 or 95% is not quite as common to get as an 80%. Or going down here, maybe these are like, 70 or 60% would be down here. And that would also say that, those values would be not quite as common as the 80%. So normal distribution means that the most common value is in the middle, and then as you move further away from that, either to the right or to the left, the values become less and less common. This is one of the most common, just kind of natural distributions that your data might take on. We call it the normal distribution. We also state that this is a symmetric distribution. It's kind of a mirror image of itself on either side. Secondly, we have the uniform distribution. By uniform distribution, we really mean that every single one of these bars is approximately the same height. So once again, thinking about the idea of test scores, if we have a uniform distribution, that would mean that basically we have just as many low scores as medium scores as high scores. So you have like just as many people getting 50s as 60s as 70s as 80s. So all of the different types of scores on the test are just as likely as each other. And if that was the case, you would have a uniform distribution. Now, the uniform distribution is very highly misunderstood because a lot of people see the word uniform and they want to think that that means all the values should be exactly the same. So, for example, someone might mistakenly think that if everyone was scoring a 75% on the test, that would be a uniform distribution. That would not be a uniform distribution. That would not even be a distribution at all. That would be like one big bar in the middle, right? If everyone was scoring exactly the same, that would just be, that you don't even have a distribution of numbers. You just have like everything is the same, right? Uniform does not mean everyone is the same. Uniform means an equal spread of the data. So just as many lows as mediums and highs. So make sure that you don't get that kind of confused. Thirdly, we have what is called the bimodal distribution. Bimodal. Bi meaning two, and modal meaning like high point, right? So we kind of have like 2 high points to the distribution, right? Or 2 peaks to the distribution, right? So if we had test scores that followed a bimodal distribution, then we would have a lot of lower values for our test scores and a lot of higher values for our test scores. I still remember my first test in grad school in my mathematical stats class that my teacher, after we completed the test, he said, oh, the distribution was bimodal. We had a lot of people who had, like 90s or higher on the test, but we also had a lot of people who did not very well, maybe like 50 or lower on the test, right? So you either did like really, really well, or you did not very well at all, and there really wasn't all that many students in the middle. And if that was the case, we would have what is called a bimodal distribution. And then we have these skewed distributions. So we have the skewed left, sometimes called a negatively skewed distribution, and then in a second, we're going to have the skewed right distribution. The way I want you to think about the words skewed left and skewed right is either the left or the right is kind of indicating the directionality of the diminishing of the bars. Okay, what I mean by that is, as you move to the left, the bars start to get smaller, right? So as I'm going from right to left, the bars are going to get smaller. And that's what we mean by skewed left. Or if we had a skewed right distribution, as we move towards the right, the bars are going to start to get smaller. It's very common for students to mix these up. A lot of times people think that, skewed left means that maybe the higher bars are on the left-hand side. But that is not the case. Skewed left means we diminish as we move towards the left, and skewed right means we diminish as we move towards the right. So again, thinking about our variable of test scores, a skewed left distribution would mean we have a lot of students who are doing really well, right? We have a lot of students who are scoring very high on the test and not as many students who are scoring very low, right? So that would be a skewed left distribution. So don't really worry about this little one bar on the right. This sometimes throws people off, but this is just to kind of exemplify that it's not always a perfect, distribution. We could have, as long as the general shape of this is that we're kind of tailing off as we fall towards the left, we don't have to necessarily have this one bar over here, right? And then we could also have the skewed right distribution, which would be the opposite. So we have a lot of lower test scores. Maybe a lot of people did very, very bad on the test, and not as many people scored very high. So the ideal shape for you as a teacher, maybe if you're given a test, would be skewed left. You have a lot of people scoring high, not as many people scoring low. And then skewed right would be maybe like a really difficult test, or one that maybe the teacher didn't teach very well. So a lot of students scored very low on that test, not as many higher values. Okay, so make sure you're familiar with the 5 different distribution shapes and you're able to identify those based on maybe a description of a variable, or at the very least based on the picture. All right, so here is a problem for you to try. In each of the following situations, determine if a normal, uniform, bimodal, skewed left, or skewed right distribution would most likely accurately characterize the data. Please draw out the histograms. I think this is very difficult to do just by thinking through it, especially if you're not familiar with histogram shapes. I really, really encourage you to actually draw out the histograms. So your vertical axis is going to be frequency, and your horizontal axis is going to be whatever this quantitative variable is, these 5 different variables. So you should draw 5 different histograms, and that should kind of help you to determine what the appropriate shape is going to be, okay? So I'll let you kind of read through these and think through those, and then we will go through a couple of them together. If you're one of my students, you'll have to submit an answer related to 1 and 3. So go ahead and give that a shot, and we'll be right back. All right, I got a little Word document here which has each of the kind of templates for the histograms. So I'm not going to completely do numbers 1 and 3, but I'll kind of set them up to some extent, or kind of explain them. But I will solve 2, 4, and 5. So the first one says the number of points scored by a player on the basketball team when the game is over. So I've got on the horizontal axis here, I have the points, and then I'm going to have frequency on the vertical axis. So what you should be thinking about for this question is, are you going to have a lot of players who score a lot of points, like over here, or are you going to have a lot of players who score not very many points, or is it going to be in the middle? Like, how are you going to expect that? Are you going to have a lot of players who are all star players and scoring a lot of points, or are you going to have maybe like a lot of players who are not scoring as many points? And maybe think about that, to think about which bars are going to be high and which bars are going to be low, and how that could be drawn out. So I'm not going to say much more about that one, so give that one a shot. That one's going to be either left skewed or right skewed. I'll just say that. Okay, and then the next one over here is the height of individuals on a first grade field trip, right? And there's a chaperone for every 2 first graders. So that we're going to have the first graders, and there's going to be a lot of those first graders, and those first graders are pretty short, so they're going to be a lot of them, and they're going to be higher bars there, and then we're going to have maybe not as much in the middle, but then we're going to have these chaperones who are going to be a little bit taller, and we have a fair amount of those, maybe not quite as many of those as there were first graders, but we're going to have a number of chaperones as well, and so we're going to have a fair amount of those. So these would be the first graders over here, and these would be the chaperones over here on the right. So this is going to be what we call a bimodal distribution, right? The number of classes attended by a student in an introductory statistics class. So this would be like, as of the end of the semester, how many classes did someone go to, right? So what you want to think about is, are you going to have a lot of students who attend a lot of classes, or are you going to have a lot of students who don't attend very many classes, or where are you going to have the most, highest bars here? What's going to be the most frequency? What's going to be the highest, the most common case, that a student attends a lot of classes or not very many classes. Once again, I'll give you the hint here. This is either going to be right skewed or left skewed. So try to draw that out to determine what is the appropriate distribution shape there. Then we have the weight of a newborn baby. So whatever the average weight of a newborn baby is, I don't know what it is, 6 pounds, 7 pounds, is going to be probably the most common, right? So we're going to have a large bar towards the middle. And then as you get to heavier babies, those are going to be less common. So like 8, 9 pound babies, they're not going to be less common than that mean or that average. And then as we go to lighter and lighter babies, those are also going to be less and less common. So this is going to be what we call the normal distribution. And then finally, we have the age of a high school student. So as you probably know, in high school, you got freshmen, sophomores, juniors, and seniors, and presumably you have just about as many students in each of those 4 different classes. And also ages kind of track pretty nicely to those different classes. So the ages of freshmen are about the same, age of sophomores is about the same, juniors and seniors. For each class, you have students who are around the same age. And since we have about an equal number of students in each of those classes, that's going to be a uniform distribution. So something like this. Sorry, I know the bars should be the equal size here, but my limitations of me drawing here with my mouse. But this would be a uniform distribution. All right, so very important that we're able to identify different distribution shapes, and that you're able to draw these basic histograms, or kind of visualize at least what the histograms would look like for all these different variables, right? So make sure you're familiar with that. You're familiar with these 5 different distribution shapes, and you're able to kind of like classify them based on a description of a variable. Okay, the last thing to state about histograms is that oftentimes histograms can be used to compare between 2 different populations. So maybe you're collecting the same variable for 2 different populations and you want to try to compare them. So here we have a variable, kind of a silly variable, which is the number of animals that a student could name in 1 minute. So you got like 1 minute, and they say, write down as many animals that you can think of. And then after 1 minute, you put your pencil down, and then you report how many animal names you were able to write down, right? Different types of animals. And so here would be a histogram for both females and males. And when you kind of stack them up right on top of each other, it allows you to kind of compare them. So we can kind of see here that the shapes seem to be relatively similar, right? We have kind of a the most common seems to be kind of in the 20 to 30 range, maybe a little bit of skewing to the left for both of them, right? But it's still, they seem to be kind of similar in shape. I can also tell that there are a lot more females than there are males, right? If you look at the scale here on the frequency, it goes all the way up to 8 for females, and it only goes up to 3 for males. So it doesn't seem like there are quite as many males that were kind of surveyed than females. So this can be a very common way that you could compare across maybe 2 different populations that you want to compare on a similar variable. Okay, the next thing I want to talk about, I didn't really know where to put this, but decided to put this here in this section because we've got to introduce it somewhere, and it kind of relates to graphical displays to some degree, is outliers. So you probably heard this term before, but an outlier would be a value that's very different from the other measurements in your data set, right? So if you have a whole bunch of numbers in your data set, and you have a couple of them that are quite a bit bigger or quite a bit smaller than the rest, then you may consider those values to be outliers. So here's just like a quick example. You have a data set that is, the numbers 1, 5, 3, 7, 9, and then you got 4,000, right? So then which of those numbers do you think, which of these does not belong, right? It's kind of like, the elementary type, question that would be asked, right? And of course, it's going to be that 4,000 would be considered maybe an extreme outlier, because it's quite a bit different from the other numbers in this little data set, right? Most of the numbers are, between 1 and 10 or so, but then we have one number that is, quite a bit larger than the rest. Now, it does become a little bit subjective to, if it's kind of close, like what if this number was, 50 or 100 or 200? Like how big does that number actually have to be considered an outlier, right? So it does become subjective to some point. There are formulas that can be used to identify outliers, but there's not really a universally accepted formula to identify outliers. I talk about that in some of my other videos, but just for now, know that an outlier is a number that's quite a bit different from the other values in your data set. Now, outliers could be indicative of a number of different things. It could be a mistake, right? So maybe when you recorded the data, maybe this was not supposed to be a 4,000, right? Maybe it was supposed to be a 40 or a 4 or something, and somehow some zeros got tacked on, right? So it could be a data recording error, or naturally, you might just expect to see outliers in certain data sets, depending on the nature of your variable. There might just occasionally be outliers, and you shouldn't really be surprised to find one, right? So an example of that might be a data set that includes the employee salaries of people who work at Microsoft. So think about that. Would there be any outliers at at Microsoft if we were including the salaries? And of course, if you start to think about, like the executive board and the CEO, a lot of those are probably making, 50, 100 million plus, whereas maybe your average software developer is only making 100,000 or something like that. So you might have, some people in the many millions, which will be considered, outliers compared to a lot of the other individuals. Oftentimes, whenever you have data sets that relate to like money or prices, like house prices or something like that, you can expect to see outliers pretty frequently. So that would be an example where maybe it's not a data recording error. Maybe you just kind of expect to see an outlier in that type of data set. And, kind of going back to these histograms, you can kind of, maybe classify some of these values as outliers. Like this person over here, what is the number here? Like, I don't know, like 5 animals. This person could only identify 5 animals, so that's kind of an outlier. Like most of the people were like in the 20 to 30 range. So this person all the way down here at only, 5 or 7 animals or whatever it is, you could say, from this histogram, we could kind of identify we might have some outliers on the low end. Okay, so previously we talked about the frequency distribution. Now let's talk about the frequency table. Now you may remember that the frequency distribution was for quantitative data. We had the example we had before was we had like the commute distance in miles, and we had the table which had 0 to 4 miles, 4 to 8 miles, 8 to 12 miles, and then how many individuals fell into each of those classes or bins or whatever you want to call them, right? Well, a frequency table is going to do basically the same thing, but we're going to have this for categorical data, right? So here we have a sample of 982 individuals in Michigan, and we have their religious affiliation, right? So in this case, the variable is categorical, which is religious affiliation, which is different than before where we had like something quantitative, like the number of miles that you're commuting to get to your job, right? So now in our first column, we have whatever that variable is, in this case, religious affiliation, rather than classes like we had before. But other than that, we're going to have this in a very similar form here. We're going to have frequency as our second column. We could call our last column the relative frequency, but I kind of opt to call this proportion to kind of link this into the idea that a proportion is just taking some kind of categorical data and taking the frequency and dividing it by the total. So I've labeled this last column as proportion, but you could also label this last column as relative frequency. So, for example, here, based on this sample, we had 175 people said that they were Catholic, which represents 17.8% of the population, or going down 58 of the individuals were non-Christian. That was 5.9%. We can calculate any of those proportions or relative frequencies by simply taking each of those frequencies and dividing by the total. So we could take 175 and divide by the total, which is 982. So we add all these together, you get 982. And you would see we get that 17.8% or so. Multiply that by 100 to find that in percent form, and to one decimal, we do get that 17.8%. So a frequency distribution, same thing as a frequency table is the same thing as a frequency distribution, but now we just have categorical data. So now we have classes instead of the classes that we had for the first column, now we're going to have what we call the levels of our categorical variable. Level just meaning what the different options are. Now, the most common thing you would do with a frequency table would be to create a bar graph, right? So here's a bar graph, kind of similar to a histogram, but more traditionally used for a categorical variable. It doesn't necessarily have to be a categorical variable, but typically a bar graph is going to be a categorical variable. So now we have all of those different categories here, the different type of religions that we had, and then the height here is going to be the frequency, which is not labeled here. Probably should have labeled that on my vertical axis, but the vertical axis is representing the frequency, how many people we have in each of those different religions, right? So kind of similar to a histogram, but the difference here is that we don't have the bars are not touching, right? So unlike the histogram, on the histogram we had the bars were right up against each other because we had the quantitative data or variable on our horizontal axis. But for the bar graph, we just have these separate categories, so we don't really necessarily have to have those bars really right up against each other or touching them because we have separate categories that are kind of separate. You could also represent this with the percentages, and that would really just be the same thing. So you're going to have the same kind of picture. So graphically it looks the same, but you could just use a different label here with the percentages. You're going to have the same kind of image here with the bars, but they're just going to be represented by percentages rather than the counts, and that's a common way to show it. So oftentimes you might have a clustered bar graph, which is going to display at least 2 bars for every label on your horizontal axis. So here's an example of graphing the life expectancy on bar graphs, and it's clustered by sex as either male or female, right? Man or woman. So we have year of birth, either 1980, 1990, 2000, or 2010. And then we have the life expectancy age on our kind of vertical axis here, right? So what this is saying is if you were born in 1980, your life expectancy apparently, if you were male, it would be 70 years. And if you were a woman, then your life expectancy would be 77.4. Or if you're born in 1990, 71.8 for men and 78.8 for women. And I have another graph over here on the right, which, just take a second to compare these two graphs and see if you can identify the difference between the two. So they actually are identifying or, displaying the exact same information, but the difference is the scale, right? So this one starts at 0 and goes up to 20, 40, 60, 80, 100, whereas this one starts at 0, and then we have this like changing scale symbol. And then we go all the way up to 65, and then we're going up by 5, 70, 75, 80, 85, here on this one on the right. Now they're displaying the exact same information, right? 70, 77.4, 70, 77.4, 71.8, 71.8, 78.8, 78.8. But the difference is just kind of the view of the graph and kind of what it looks like visually to us based on the changing scale on our vertical axis on this case. And this is something that you really should watch out for whenever anyone displays a graph to you, because anytime there is a changing scale like this, that can sometimes distort the graph to some degree. What I mean by that is, if you have a changing scale, then now the numbers on your vertical axis or your the length of your bars are no longer proportional to what the number is. What I mean is that ideally, like if you had a number which was twice as big as another number, that would equate to a bar that was twice as big as that bar. But if you're going to be, messing with the scale in this way, jumping over a whole bunch of numbers, going all the way from 0 to 65, that's no longer going to be the case. And you can see that in this graph on the right? So this bar right here of 70 is about half the height of the 77.4, a little bit over half the height of the 77.4. So you might kind of instinctively think that this blue bar would be representing like half the number. But if you look at the number, 70 is, much more than half of 77.4, right? So, just looking at the bars, it might lead you to believe there's a lot bigger difference in the life expectancy of men and women than there really is in reality. So you really should be watching out for, whenever anyone presents a graph to you, especially a bar graph, that changing scale on the vertical axis. Because if there is a changing scale on the vertical axis, that's really distorting the graph, and now the bars are really not completely doing justice to the numbers, right? I would pay more attention to the numbers in this graph on the right rather than the bars. So I would prefer this bar graph. I would prefer this bar graph on the left to be presented to me, because the one on the right is really distorting the differences between the life expectancy more than they really are in reality. So once again, this is a clustered bar graph, or these are clustered bar graphs, and they are clustered by gender because we're showing different genders or sexes on our, clustering them together on our horizontal axis, right? And the squiggly line here on the right graph is indicating what we call a changing scale. We're kind of jumping up here, which I would try to avoid if possible, right? It's always going to be a better graphical representation of your data if you can avoid that jump scale. Here are some more egregious examples of this with just some made-up data here. So we have, some kind of marketing department or something putting together the sales for different maybe locations or different groups, right? So let's say that you're in group D, right? And so maybe if you are in group D, you would prefer the graph on the left rather than the graph on the right. So once again, we have the same kind of deal here, that they're displaying the same information, but we have different scales. So this one starts from 0 to 2,000, 4,000, 6,000. And this one starts at 8,300, 8,400, 8,500. So this one doesn't start at 0, and this one does start at 0, right? And this one's going up by hundreds, and this one's going up by 2,000s, right? So if you're part of group D, then you're probably going to opt for the graph on the left, right? Because this one makes it look like you're doing a lot better than the other groups, right? Whereas in reality, you're at just over 8,700, and group C is like at 8,650. So there really is not all that much of a difference between these four different groups. But the way that the graph has been displayed here makes it look like if you're part of group D, that you're doing so much better than the others. Once again, the bar lengths are not proportional to how big the numbers are, right? If that was the case, then the A group should be like less than half of the D group, right? The D group is like 8750, and the A group is like 8450. That's not half of D. So this is not really, accurately representing the numbers on our graph. And that's really the point of a graph, is to, better enhance or help us to understand the numbers. So I would not agree with this graph on the left, and I would not opt to ever use a graph like this on the left. I would more opt to use the one right over here on the right. Now, you might say, well, this one doesn't look as fancy. It makes it look like all of the groups are, really close together and doesn't really, show the difference between the four groups. But that's the point, right? The four groups really do not have that much of a difference between their sales. So you really should not be showing much of a difference between them if there is not a difference between them, right? It's more accurate to show them as really looking very similar to each other rather than kind of exaggerating those differences. So, go with graph number 2, don't go with graph number 1. So my note here is the graph on the left really should have that changing scale symbol. Even with the changing scale, the chart on the left might be considered to be misleading, for sure. I definitely would agree with that. Now I have a few different real-world examples for you. So here is a post from President Joe Biden's Facebook page where he was showing the eligible unvaccinated American adults both before a vaccine mandate for government employees and then sometime later after that. So we can see that 95 million people were eligible for the vaccine in July, and then sometime later there was only 67 million eligible Americans. So kind of the point of this graph was to show that this vaccine requirement is working, right? That's what their message here, and that a lot of people are getting vaccinated after this kind of announcement, right? But once again, if you look at the scale, you can see that the scale starts at 50 million. So that means that the bars are not really proportional to the numbers, right? So if you look at the bar on the right, it's less than half of the height of the bar on the left. But the number is not less than half of this number, right? 67 million is not less than half of 95 million. So once again, this is somewhat of a misleading graph. And maybe a better way to display this would be to start your scale at 0, right? So if we start our scale at 0, then this is what our bar graphs would look like. So we would still have a fair difference, 67 million compared to 95 million, but this puts it a little bit more into perspective. Now the bars really are proportional to the numbers. Here I have one more example. This is from Fox News, back when Tucker Carlson was on there. So we have the percentage of Americans that identify as Christians. And once again, we have a scale that does not start at 0. So once again, anytime you see a scale that does not start at 0, you should be paying more attention to the numbers than really the heights of the bars, because the bars are really not doing justice to the numbers. The bars are not going to be proportional to those numbers. And we can see that here. In 2009, there were 77% of people who apparently identified as Christian. And in 2019, according to this Pew Research Center poll, only 65% of people identified as Christian in America, right? So the idea here is that, there's a huge decrease from 2009 to 2019 of the percentage of Americans that identify as Christian. But the bars make it look like a much more dramatic decrease than there really is in reality. A more accurate way to show this bar graph would be to start at 0. I know I don't have the scale here, but this would be a scale on the right that would start at 0. So that still is a fair decrease from 77 to 65%, but you're only distorting the numbers and kind of misleading if you don't start your graph at 0, right? This is making it look like a much bigger decrease than there really was in reality. All right, so one of the last things to talk about here in this section is the pie chart, which you are no doubt familiar with. So a pie chart is going to display a categorical variable, either with percentages or counts. And if there are too many categories, then the pie chart can get a little bit messy and difficult to read, and you might want to opt for some other type of graphical display. So here's an example of a pie chart for just some made-up data related to preferred music genre. So we have all these different music genres and the percentage of individuals who said that that was their preferred genre. Now, the percentages on a pie chart really should add up to 100%. So sometimes you might have a survey question where more than one answer is possible, and that might create a situation where the totals add up to more than 100%, and then really you should not be using a pie chart. But that does not stop people from doing it. So here's an example. Americans who have tried marijuana from a CBS News poll. 51% today said they had tried marijuana, 43% last year, and then 1997 there was 34%. So it should automatically feel pretty weird for you to see a pie chart where one of the slices is 51% and that doesn't even make up half of the pie. So I'm not sure how this, really made it into their news broadcast here, but this is an example of, maybe a pie chart that you would not want to use. So I'm not sure who this person is, but they tweeted about this, Dorsa Amir, and they said, first of all, it's a pie chart. Second of all, the total is greater than 100%. So if you add up all those, they add up to more than 100. The relevant categories are today, last year, and the year 1997. So kind of pointing fun at like, why are you going so far back into the past? Is it really make sense to, compare that? But I guess they're kind of wanting to show the contrast, I guess, from today all the way back to 1997. So maybe there could be some criticism there. And maybe something that you did or did not pick up on, the margin of error is actually listed as the source. Let me go back here. You can kind of see it a little bit better. MOE stands for margin of error, which they're saying as plus or minus 4%. But that's not your source. Your source should be like, where did you actually get this data from, right? The margin of error is like realistically how much you could expect these numbers to be off by. So that really shouldn't be your source, but somehow that made it in there as the source. So then we could ask ourselves, really why do these numbers not add up to 100%? And most likely because, definitely because these are not really related categories, right? These are just like completely separate surveys, and there's no reason to think that the total of all these surveys together would add up to 100%. So really, you probably should not be displaying this in a pie chart. Maybe some other kind of graphical display, maybe a bar chart would be better to display these numbers. So I have one more example here of a misused pie chart, biggest COVID-19 worries. So we have, back in 2020 when this was more of a, pressing topic, people were surveyed and asked, what's your biggest worry about COVID-19? Either getting it, your family getting it, or the economy. And once again, you can see that the percentages add up to much more than 100%. So it should look very weird for you to see a slice of the pie that is clearly less than half the pie that is displaying as like 68%. That should, look very, very wrong. Or like this one's like, a quarter of the pie and it's displaying as 48%. So something clearly went very wrong here. So no, what are you doing? If you're the reporter here and you were displayed, you're given this graph and you're supposed to, you're on air and you're supposed to talk about this. Do you try to fake like it makes sense, or you call it out on the spot saying, this pie chart seems kind of weird. So, but anyways, what's the reason in this case why these percentages do not add up to 100%? Well, most likely because individuals were able to select more than one category, right? I could say that I'm both worried about getting it as well as my family getting it, right? And when you have the opportunity to select more than one option, then that's going to create a situation where the totals are going to add up to more than 100%. So really should be avoiding the pie chart in that type of situation. Maybe a more appropriate way to display that data would be with some sort of bar chart like I have here. And it would be more acceptable for those percentages not to add up to 100%. All right, I think that completes everything I wanted to talk about here related to graphical displays of data. This is by no means every single different way you could graphically display data. We'll be talking about some other ways to display data in other sections here, but these were just some of the more common ones. So hopefully you were able to get something useful out of this, and I will see you in the next video.